Welcome back to the Introduction to Machine Learning. In the previous video, we pre-processed our data. Now it's time to train our machine learning models. So questions you might have could include, how does one train machine learning models in Python? And what machine learning models might be appropriate? So we're going to train a random forest and a neural network. First, let's discuss a random forest. This diagram shows a decision tree for classifying 3 different types of iris flower species. You can read more about decision trees in this Wikipedia link. So a decision tree asks a number of questions. First question here being, is the petal length less than 2.45 centimeters? If the answer is yes, then the decision is that it's a setosa. If no, then there's another question, is petal width less than 1.75 centimeters? If the answer is yes, then it's versicolor, and no, it's virginica. So this looks something like an upside down tree with the roots being up here and the branches down here. That's a decision tree. Then a random forest, which you can read about here in Wikipedia link, uses ensemble learning with many decision trees to make better predictions. So random forest is considered black box, where a decision tree is considered white box. Let's discuss a bit more about this. Decision trees are intuitive and their decisions are easy to interpret, called white box. Random forests, on the other hand, or neural networks, are generally considered black box. They can make great predictions, but it's usually hard to explain why the predictions were made. On the other hand, decision trees provide nice, simple classification rules that can be applied manually if need be. The diagram below represents random forest. There are 1, 2, 3, 4, etc., up to B decision trees. And each tree, tree 1, 2, etc., etc., up to tree B, so tree J, makes the prediction that a particular data point X belongs to the class Kj. So K1 here, K2 here, Kb here. Each decision tree has a varying level of confidence in their prediction. Then, using weighted voting, all the predictions K1, K2 up to Kb are considered together to generate a single prediction that the data point belongs to class K. Let's take a quick aside on wisdom of the crowd. Suppose you pose a complex question to thousands of random people, then aggregate their answers. In many cases, you'll find that this aggregated answer is better than an expert's answer. This is known as wisdom of the crowd. Similarly, if you aggregate the predictions from a group of predictors, you'll often get better predictions than an individual predictor. A group of predictors is called an ensemble. In the previous page, we created a training and testing set. Now we can use these data sets to train our random forest. So we import the random forest and a function called accuracy score. Then we train our random forest classifier with a criterion called Gini, max depth of 8, which means the number of sort of layers here. So this is 1, 2. Number of estimators, so how many trees, and then set the random seed for reproducibility. Then the random forest is fitted to the training data, and then predictions are made on the testing data. Then we can make an accuracy score of how well it's done. So it's got about 80% accuracy here. Now we can move on to a neural network. First, let's import the bits we need for our neural network in PyTorch. Next, we make variables for a number of neural network hyperparameters. Now we want to create tensors, first of all, for the training data, then the training labels, then create variables out of those tensors. An important thing for neural networks is to keep some events for validation that the hyperparameters that have been chosen during training are useful, are good. So we keep some events for validation, the first 100 events here, and then the rest of the events for training the neural network. Then a tensor dataset for the training and validation are defined using the data and labels. Then a data loader is defined, which is going to be useful later when we want to load the data during our training loop. Here we define the neural network that we'll be using. It's called a multi-layer perceptron, otherwise known as a fully connected neural network. It's got a hidden layer with number of neurons, hidden dimension, find here. The order of layers for a forward pass through the network is specified here, and each fully connected layer is followed by a ReLU activation function. Then the function returns an unnormalized vector of outputs x and a vector of probabilities for x, calculated using the softmax. Next, we need to define our classifier, the number of input dimensions, hidden dimension, and output dimension. Then we specify which optimizer we're going to use. Here we're using stochastic gradient descent, but you can try other optimizers later if you want. Now this cell contains the training loop. So let's copy and paste that in. And as it's training, we can discuss it. We loop through the full training dataset multiple times. Each loop is called an epoch. However, we don't read the full dataset in at once during an individual epoch. Instead, we split it into batches and use the optimization algorithm to update the network after each batch. The train loader here breaks up the full dataset into batches automatically and allows us to load the feature xtrain and the label ytrain for each batch separately. Because we specified shuffle equals true when we defined the train loader here, the full data sets will be reshuffled every time on each epoch, so that we're optimizing over an identical sequence of samples in every loop. The neural network module can be set in either training or evaluation mode. For the loop we've defined here, it doesn't make any difference as we do not use any layers that perform differently during evaluation. However, it's included here for completeness. So let's see how it's doing. It's on the 6th epoch at the moment. It's printing the training loss after each epoch and the validation loss and the validation accuracy. So with each epoch, the training loss seems to be going down, and so does the validation loss. They're both kind of leveling out at the moment, and the validation accuracy is going up, but it's also kind of leveling out. So we wait for that to finish. As we wait for that to finish, we can keep going on. And this is how the neural network predicted labels can be obtained. So as before, some tensors are made for the testing data and labels. This is very similar to what was done for the training up here. Then variables are made for the testing, similar to what was done here. Then, similar to what was done here during the training loop, the output of the neural network and the probabilities are obtained on the testing set, and then an array of predictions is obtained and the loop has finished training there. So we have a challenge for you. Once you have this YPredNN, see how well your neural network classifier does using accuracy score, which you've already done for the random forest classifier. So take a look back there if you need. Your neural network should have a similar accuracy score to your random forest, but also note that accuracy is a naive metric. Suppose you have a data set where 90% of the data set is background and 10% is signal. Now, suppose we have a dumb classifier that classifies every data point as background. This would mean it would have 90% accuracy, which demonstrates why accuracy isn't the preferred performance measure for classifiers, especially when dealing with skewed data sets, which show up all the time in physics, where you have more access to background than signal. In this tutorial, we're using 520,000 background and 165,000 signal. So that's it for this lesson on model training. And the key points being that random forests and neural networks are two viable machine learning models. So see you in the next lesson where we're going to check for overfitting of our models.